the objectives for cutting tool design. So if you think about it, for most cutting tools, I mean, I would say just about all cutting tools, your objective is to do some sort of subtractive process and remove material, and then you get some sort of different part, and that is what we call machining. Okay? And, that machining can take all kinds of different forms of cutting, but generically that's what we would call machining. And when we do any sort of machining and we pick different types of tools, we have to understand the physics of metal cutting to select the correct tool for the job. So, in general, one of the basics of the physics of cutting metal is that your tools need to be harder than the workpiece. Okay, if you are trying to cut, some really hardened tool steel, you're not going to be able to use a wooden tool to cut that, right? So, and we also have to understand the physics of how much power do I have to input at a given rate in order to maintain a cut the way I want it to cut. And also, I need to understand the physics of how much forces are going to be involved so that I can maintain the rigidity and the structure I need in the tool and even the workpiece itself in order to cut it, right? Because if you kind of hit a workpiece too hard, you might break the actual workpiece. If you grip the workpiece too hard to hold on to it, you might crush it. These are all kinds of different things you need to do to figure out how to use the right tool and right tools for the job. The other thing is we have to understand what the most economical tools are for the job. So, if we have some job, and let's say our job it's a $1 million job, so we're gonna get $1 million for this job, and that's what we're gonna walk away with. If we spend $5 million on the tooling, then this is not going to work, right? You're not going to necessarily be able to spend more than you make on the job. Okay, so if you think you're going to make $1 million on it, you're going to need to think about how much am I going to actually have to spend to get there, right? So you need to spend money to make money, as it were, but you can't, if you have a certain margin and you say, well, we could do this really cool tool. If that tool eats up all your margin, if you have all this tooling and you're going to make $1 million and now you add $5 million worth of tooling that you weren't expecting to, because you say, well, it works better. Well, maybe it eats all of your margin and now you're in the hole. So now, you're not going to do that. So the tools have to be economical. That's a big deal. And that's usually the trick, because the trick is usually, it's you have time and you have material and you have limited amount of money. So usually it's trying to spend the least amount of money the fastest so that you can get that product out there as fast as you can. And then also you want to consider how you can use compound processes. And basically what that means is you want to see how you can make things more efficient. So if you can use one tool to make 10 features, that's usually better than having 10 tools make 10 features. So that comes down to oftentimes, the design of the part and designing for manufacturing. And so you're going to want to consider that, right? So if you only needed one tool in your shop, then you could make every single part you'd ever want to make with that one tool. That would make your life a lot easier. If you have to have 1 million different tools, to do thousands of different jobs, well, now you have to manage all those tools. Then you have to keep track of them, and you have to, understand the nuances of them and how they work differently and have different holders, and, things get complicated quickly. So you're never going to have a situation, or rarely would you have a situation where you're going to have just one tool that does everything. But there are oftentimes a lot of cases where you can, by, doing some figuring, figure out that, well, actually we don't need all these tools we thought we did. We can actually make our life a lot more simple. And usually that simplicity can be translated to cost savings and time savings, which a lot of times are the same thing. So And then here we have machining in slow motion, and we'll talk about that briefly here. Okay, so here we have machining happening in slow motion, and we can see, stop this, we can see the tool here. There's the nose of the tool, and what we're seeing here is a side view, and beyond that side view, this is the side of the tool, and this is actually the chip that's being formed. So here's the surface of the material, and the material is actually plowing up the front of the tool. Okay. And if you look at the front of the tool, you'll see what's actually the nose of the tool. Okay, and here we have the relief face of the tool because we don't want to rub. And what you're seeing appearing there is what is called built-up edge. And that built-up edge you'll see will form, and then it will break away and go past. Okay, and this area here, this shearing zone, this crush zone, this is where you're getting your plastic deformation. So some of the material underneath is actually being crushed plastically, but some of it's being crushed elastically, and it will kind of snap back. But in this area is plastic deformation. And if you notice, if you draw a line across here to the top of the material, the thickness here, the chip is actually thicker than the depth of the cut. Okay. And you can go in the notes and you can watch this video and you'll see what I'm talking about. And we've talked about this in class, and this is a good, if you take your book and actually open your book up to your cutting tool design pages and you look at the pictures while you're watching this video, I would say that's actually really helpful too. And again, the book is very good and it goes through the details of all this. But I think having the video and looking at it happening, obviously this isn't very much slowed down speed the way you're viewing it, but I think it's pretty helpful to do that. Okay, so the elements of machining. So your book will talk about the 5 elements of machining, and that's your cutting tool, your tool holder, your work holder, your workpiece, and your machine. And if you think about it, and we've talked about this already in some detail, but when you're doing machining, the interrelationship between all these things, there's a lot going on. So, if you have some sort of, let me change some of the colors on my thing here. So, okay, so we have some sort of table, and that table, we'll say that can move, and then here's the base of the machine. Okay, this is my basic machine interaction here. Okay, and let's do this, and then let's change some of the colors here. So we have some sort of workpiece, and then let's see if we can draw this, and then we have some sort of tool coming down. Oh, that's not what I wanted to do. That's okay, we'll fix it. Okay, there we go. And we have some sort of tool coming down. Okay, so in our example here, in our fictitious example, so we have from the tool, which is the red one, to this green part, which we're going to call is the workpiece, you have this chain. So the tool goes to the spindle, which goes to the machine. Okay, and then the machine goes to the table that's on the machine, and then we'll call this blue thing is the fixture, and then from the fixture here's the workpiece. Okay, so you see you have all these elements linked together, and right where the red tool and the green workpiece come together, that's where the machining happens. That's where that slow motion video happens. Okay, That's where the material is cut away. There's a lot going on there. If you think about it, you have this big, huge, expensive CNC machine, and it's got all this stuff bolted to it and on it, and all this high precision stuff, just so that that little cutting action can occur right there at that interface. Okay, so you have all these things working together, and the interrelationships there and what's going on. It's a considerable amount of things going on, and what that means is there are, usually if there are a lot of parts in the chain, that means there's a lot of places for error. So if you have a machine or a machining setup that's not working, there's a lot that can be going on there. Okay, so you got to consider the design of all those pieces. So metal cutting, and we're going to be talking about metal cutting primarily in this course. Although you can machine, it's possible to machine polymers, and that happens all the time. That's a common thing. But we're mostly going to be talking about metal. So the cutting tool, or the cutting tools we're talking about, for the most part, are designed to shear metal away from the workpiece while minimizing rubbing contact. Okay, in our video we saw where you have the tool and you have the workpiece, and here's your tool is kind of, here's like this, and then the tool comes back up, and then you had this area here where you had your chip forming, and this is the tool right here, and you had this interface right here. Okay, the area underneath of here, and let me just add some color to it so we can see. This area right under here is actually clearance. You don't want it to rub there, and you don't want it to rub because if it's rubbing and it's not cutting, it's just generating a lot of heat and friction, or it's generating friction, which generates heat. So you don't want that. Okay, so you want to minimize rubbing, but you have to be careful when you change the rake angle of the tool. You can only change it so much and so far before you start to lose other things. Maybe you lose strength, or you lose your ability to roll a chip, or you increase the ability till you don't. So everything is kind of a trade-off. So you can change things about the tool, but usually, if you improve one thing, maybe you decrease something else. Okay, and there's a whole science behind this, and we'll spend a lot of time talking about it. Your book goes into detail of it, and some of the websites I point you towards, like Kennametal. If you go to Kennametal's website, and Kennametal is that's a company that makes cutting tools. They're huge, and they make all kinds of cutting tools. They have all kinds of resources online. You can get a job doing just designing cutting tools and testing them. There's a lot of work that goes into that. But each little minute change you make makes a difference. And the totality of those descriptors of the tool are what we call tool geometry. Okay, and changing the tool geometry is the best way to kind of change what you're getting out of your tool as you're trying to manipulate it. So here we come down to a good picture that shows what we were watching happen in slow motion. Okay, and essentially this is a single piece or a single point cutting tool. So really, if you think about it, this is kind of more like a shaper tool or a turning tool that was zoomed in on, so that the arc is such a small little differential element that it looks like the tool is moving along a straight line, or the workpiece is moving along a straight line and not actually rotating. But for an instant in time, this is how all cutting tools work. So even an end mill rotates, but if you took a freeze frame of the instant the end mill starts cutting into the material, and you looked at the tooth as it engages the material up close, and you just looked at it over a very small amount of travel, it would behave just as this picture describes. Okay, you'd still have the chip thickness, and you'd still have the layer being removed. You have a width of the chip. You'd still have a rake angle. You'd have a direction of prime motion. You'd have a flank angle. You'd have a cutting wedge, and you'd have the resultant machine surface. Okay, so and your book has some really good examples too. This is why I think it's good to see the video of the machining happening in person, so that you can kind of look at how this all kind of comes together. Especially if you aren't a machinist, I know some of my students are machinists, some aren't, and that's okay. But if some of us have a little more familiarity than others, but if you understand this picture when you're looking at an end mill cut or even a turning tool cut, this is really what's happening. Okay, so orthogonal versus oblique cutting. So orthogonal cutting has a cutting direction that's perpendicular to the cutting edge. And oblique cutting is when the edge is at an angle. Okay, and a large part of making the chips is controlling how to get rid of them. So again, we said the cutting tool must be harder than the workpiece. That's part of the physics of the thing. And then there always has to be a little bit of interference actually between the tool and the workpiece, right? So if there's no interference, then you're just cutting air. You never actually cut the part. So the tool actually ends up running into the part. And the relative motion between the two has to happen in such a way that you actually get enough force that you can actually tear the chip off, because you're shearing the chip just like you would shear if you use a pair of scissors, and you're shearing material. It's the exact same process, right? So you need to input a pretty great deal of force, and then you need to be able to sustain that throughout the cut. So there are two types of chips. There's continuous chips and there are discontinuous. And continuous chips are bad. So usually you want to get rid of continuous chips. Sometimes it's difficult based on the physics of the way the chip is being formed, given the strength of the material and how it's hardening as it's being cut and the speeds that you're cutting at. Sometimes it's hard to actually break a chip. And, for those of you who are machinists, you'll know exactly what I'm talking about. And for those of you who aren't machinists, you'll just have to take my word for it that certain materials, when you cut them, they get stringy and they don't want to make pieces. Okay, but you always, just as a general rule, just know that you always want to make a chip. Okay, that's discontinuous. And the best is when they break into small, tiny little pieces. And the best chips are ones that they call them, it'll be 6s and 9s. So the chips will actually look like that. Okay, and you'll have a whole mess, a whole pile of those laying around everywhere when you're done cutting, and they should have a shape that looks just like that, and they should have a color to them, and usually they have like a light straw to maybe like a blue color, and that's the heat that goes into the workpiece making them change colors. Okay, and the reason why you want discontinuous chips is because they're easy to flush away from the workpiece and they're easy to control. So long stringy chips, one of the things that will actually end up happening to them if you're cutting long enough is that they'll get recirculated in the cutting process, and they can get jammed between the workpiece and the tool, and that it'll cause surface finish issues, and it can also cause dimensional instability, because you could have this work hardened chip get lodged between the nose of the cutting tool and the workpiece and actually push the tool away. So at that instant in time, the tool's not cutting properly. So it's usually a problem. That can happen with chips that are broken up into discontinuous chips as well. You normally need to flush them away quickly, but if you have long stringy chips, it's a much more likely scenario. So built up edge. So we saw that built up edge on the tool where the nose of the tool was something like this. And, we had I'll just keep drawing it this way. So we had the base of the part was like this, and then we had the chip sliding up the wall of the part, and the chip was moving up here, and you had this little gap area there. And I think if you were looking carefully, you noticed that there was like a little material would get lodged here and kind of not move. This would all be sliding by, but this little ball of material would kind of sit, and then once in a while it would break away and kind of, move down here. As the tool, the tool is moving this way, the tool moves past it. That's called built up edge. Okay. Pardon me. And sometimes it can actually increase your tool life because it can actually kind of buffer the nose of your tool, but it can actually cause a lot of problems. And generally you don't want built up edge. And the issue with the dimensional stability can come in because as you're cutting, if you have that little built-up edge occur, it can actually push the tool away, and then the tool will snap back, and that can actually happen with some sort of frequency, and it can cause a dimensional problem. Okay, and also that can damage surface finish because you can drag that lump of material across the part, and it can leave a bad surface finish. And I'd encourage you to watch that video in the notes on that topic. So the mechanism of chip formation. So cutting generates heat. Okay, that's the mechanism of chip formation. You should watch that video, and that will be really, really helpful. But cutting generates heat because there's a lot of friction and there's a lot of energy being input into the system in order to get that material to tear, and some of it turns to heat. And so that's something to be aware of. So that's a lot of times why we have coolant on our cuts, and we have to be careful that we don't overheat, because if we overheat, we'll actually get chemical degradation of the cutting tools. The other thing to be aware of is that the chip is usually thicker than the depth of cut, because the chip actually gets compressed and the pieces slide diagonally along one another and they stack up. And that the chip is thicker than the depth of cut can tell you a little bit about the actual cutting that's going on. And you can actually approximate the shear angle by measuring the thickness of the chip. And it's the optimum range is somewhere, I think, around 1.5. And the range is equal to T1 over T2. Okay, and the chip is actually also harder than the workpiece because it work hardens, it strain hardens when things are happening, when things are being cut. All the slip planes move. That's why it actually slides and gets thicker. Okay, and when you're looking at chips can tell you a pretty large amount of what's happening. So if you're doing any sort of cutting process, it's a really good idea to capture your chips and then analyze them afterward and see how things are actually working out. Because most of the time when you're cutting, you're using some recommended speeds and feeds in order to be able to cut, but they may not be optimum for your given setup. So one of the best ways to analyze what's actually happening is to capture your chips when you're done, and then kind of look at them and deduce from them what's actually occurring. They'll tell the truth of what's going on. So tool velocity, the velocity of the tool, that's the speed of the tool relative to the workpiece. So remember, I said it's an instant in time, and it's the relative motion. Okay, so it doesn't matter whether you're looking at a lathe or a mill. The instant in time where the tooth of the tool is engaged in the workpiece and the differential speed between them is the tool velocity. Okay. The other thing is to realize is that velocity is proportional to temperature. So the faster you go, the more heat. And so that's why they say in machining world, speed kills. So if you go too fast, you heat up too fast and you wear things out. So why would you go faster than if it wears your tool out? Well, because sometimes it's easier to machine things if you go faster. So there are some materials where if you cut too slow, you'll work harden them and you'll create a continuous chip, and you won't actually be able to break it because your yield strength is not going to allow you to actually break that chip. But if you cut really fast and you heat the chip up locally, then you might be able to actually rip it into pieces. So you kind of have to sometimes play with things and see if you can figure out how to get them to actually cut. So the cut size, that lengthens the contact, but it doesn't increase the force per unit length. So basically, if you think about it, if the nose of that tool goes deeper into the part is what we're talking about here. So that's where depth of cut is quote unquote free. So essentially, if you're doing some sort of machining, you want to change the depth of cut to as deep as you can possibly cut while you're cutting. Otherwise, you're just wasting time. Okay, and your feed rate, if you increase your feed rate, essentially what you're doing is you're trying to cover the same amount of ground in a shorter amount of time. So you're going to have to increase the force to do that. Okay, and that's where you can mechanically break chips as well. Not only can you get the heat if you increase your speed, But if your feed rate, how much you're grabbing per tooth, sometimes you can break more because you can get some distortion that happens. So cutting fluids. So your book's going to talk a lot about cutting fluids. You can please read about all that. And cutting fluids are usually, generally think of them as a way to lubricate the interface between the chip and the tool, and to reduce heat loading. Okay. And also one thing to remember is if you're using coolant, usually you want to keep the coolant on, either on or off. It's not good to do intermittent coolant, okay, because you can cause thermal shocking and then you get cracking. So tool wear is a fact of life. Everything wears out. We wear out. It's just a matter of time, right? And tool wear, each tool has a given amount of life. So depending on how you use the tool, you can increase or decrease the life of the tool. And in each case, cost is going to be what drives that, right? So if you can do your parts much, much faster and sacrifice a little tool life, you have to make the decision based on the data that's in front of you. If your tools are cheap enough, then that might be okay. But if your tooling is really expensive and increasing your speed wears them out faster than is acceptable, then you might have to go a little slower. Okay? And when the tool has reached the end of its life, you're going to have some sort of breakage, basically. Okay? But usually a tool failure is also going to be defined as some sort of either surface quality or dimensional stability problem. So if you have some sort of tool and you're given a certain amount of wear that you can compensate for, once you've exceeded a certain amount of wear compensation, even though the last part that came off the machine was good, the tool would be considered failed. The tool would be worn out. So it doesn't mean you couldn't get maybe another part or two out of it, but you don't want to get into a situation where a tool is actually breaking in a part while you're running it. That's a real failure. But whenever, if the horsepower suddenly spikes in the machine and everything else seems fine, it might be that the tool is worn out to the point where you're having to add that much more power to get the parts, the chips to shear, and that tool would have failed at that point. So heat and pressure essentially, are the things you're up against, and they both have their own ways of doing things. Plastic deformation is a combination of both, but if you have sustained pressure on the tool, you can actually deform the edge of it. The chemical reactions generally occur due to the heat, and along with the chemical reaction, that can speed up the diffusion between the workpiece and the tool material. So essentially the chemicals in the tool to the workpiece or vice versa can leach into one another, or you can either leach them out of the tool, or the material in the workpiece can actually leach into the tool and actually break it down, and then wears out. So both heat and pressure are generally the issues you're going to have. You can have things like vibration could wear the tool out as well, but the vibration might be, you might call that a form of pressure, effectively, is how it would manifest. So abrasive contact, which is more of a pressure problem, that's where it actually mechanically damages the tool. So the coatings that are on most tools are layered in such a way to provide heat resistance, and they also provide some sort of wear resistance. But eventually they'll break, and once they start to break down, then the tool will start to break down really quickly. Okay, and most of the time that happens abrasively. Certainly, if the tool's dropped or damaged before it's being used, you could have some sort of flaw in the surface, and then from that flaw, once you provide the pressure of the tool as it's cutting, that area could grow rapidly and the tool could fail quickly. So if you have sustained pressure at the tool tip, then that's when you can get the plastic deformation. And depending on the type of material you're cutting, the tool geometry will actually be altered to give you the best edge for the type of material. And remember what I said earlier, if you change your relief angles in your tool to provide more clearance, you might actually be making the tool weaker, as it were, and it has less support to resist bending. So that, everything's a trade-off. It might cut better, but then in the same hand, it might have more issues with maintaining sustained pressure before it actually plastically deforms and breaks the tool. So as the temperature increases and the tool is worn, the workpiece, depending on what it is, can actually chemically react with the tool. Okay, so heat is never usually a good thing. It can soften, it momentarily softens the chip, and actually, if the heat can all go directly into the chip, it's actually a good thing. So, the chips actually kind of provide a secondary purpose as they're being of actually carrying away that heat. And, between the coolant and the chip, hopefully the tool temperature can be kept down. And, that's the best way to keep the tool life the longest generally. And, sometimes you want to cut your parts softer versus harder. In general, I would say from a manufacturing standpoint, you generally don't want to heat treat after you cut things because you lose dimensional stability, but sometimes they have to be cut. Although today, what used to be considered too hard to cut years ago today can be cut. So, nowadays you could machine 45 Rockwell or 50 Rockwell parts, whereas maybe years ago that was not a thing. You couldn't really do that. So, but there may be a case where you want your parts softer to prolong your tool life. In general, I would say the tooling cost as a fraction of the entire project is probably small enough that in general nowadays with modern tooling, you'd want to just cut parts hard actually. But it is a strategy that's available. So ultimately, you need to keep your setup rigid. So that picture we drew earlier of the machine, the link from the tool all the way through to the material, where it was like the sewing machine looking device that I drew. This sort of thing. And then you have your drill sticking down there, and then you have your workpiece, and it's all cutting together. That whole setup needs to be super rigid, right? If there's any slop or any movement between the parts, then you're going to have some issues, and you're going to have vibration, you're going to have movement. So the instant in time where that tool is engaged with the workpiece and that chip is being formed, rigidity comes into play and is very important. Okay. So whatever's your weakest link is going to guide your process. So what that means is, if your tool is your weakest link, then, as you're cutting, if you speed up or you import more a higher feed rate into the tool, eventually the tool is going to break. Ideally, you probably don't want your fixture to just snap off. Okay. So, but that's something that has to be considered. And your speeds and feeds, they need to consider all the details of your material and your tool size and how much power. So basically, the amount of power you can input into your system in a sustained way is going to tell you how fast you can cut. So once you've cut enough material, if you can't add enough power, you'll slow the machine down before you won't be able to sustain the rate that you want to sustain. Okay, because each time the tool engages in the cut, let's say it's an end mill, each chip that's torn away from the material or sheared away from the material absorbs a little bit of power that the motor is actually putting into that cut. So if you're trying to take more cuts than the motor can input power-wise, then you'll just slow down, right? So it's kind of like when you're in your car and you're hurtling down the highway. Once you've got the pedal to the floor, you can't go any faster, kind of a thing, right? And if suddenly there was a great deal of drag on your car for some reason, you drove into a big headwind or something like that, your car would slow down proportional to the headwind because you don't have any more available power in your engine to exceed that amount of drag that's being put on your car now, right? You can think of it that way. So in that drag, in essence, in your machine is your feed rate, essentially. So your material removal rate, your MMR, is going to be in some way proportional to the type of material that you're cutting. It's going to be proportional to the material and the machine times the machine. Okay. And if your material gets that much stronger, then you're going to lose for your material removal rate. Okay. So then we just have a couple details of up some tools. So drills. So drills make holes, and drills. It might seem pretty straightforward, like, oh, okay, yeah, drills, sure, they make holes. You can have an entire career just designing drills. There's a lot that goes into drills. But we're just gonna, for now, we're kind of go over this in the course of doing all kinds of tool design. But drills make holes, and generally when we talk about drills, we're talking about twist drills. So it has helical flutes along its edge, and those flutes are designed usually to just get material out of the way. So they kind of auger the chips out. Okay. And usually a drill has a point something like 118 degrees, and usually other than 180 degrees, although nowadays there are some really good flat point drills that have good uses and work really, really well. And on a drill, one thing that's important to remember about a drill compared to an end mill or something is drills only cut at the very tip of the drill. So what are called the lips of the drill. The lips of the drill cut, nothing else cuts. So the sides of the drill do not cut. So there are certain drill mills and certain specialty tools that are kind of a combination of both. But a drill cuts at its point and along the lips, and that's it. It does not cut along the sides. So, you're not going to mill with a drill, okay? And they can be made in high-speed steel or carbide, or even you can have a high-speed steel shank with a carbide tip. That's pretty popular too. Once you get above a certain size, the cost of the carbide is unacceptable. And now you need to have some sort of high-speed steel shank with a carbide tip that can be replaceable. That's called an indexable drill. So an end mill. Kind of looks like a drill, but you use it for side cutting. Okay. And unlike a drill, most end mills, even if they're center cutting, you don't really want to plunge straight down with them. Okay. If you already have a hole made and you want to open the hole up, now you can plunge down through because you're not actually cutting on the center. But on an end mill, you don't want to cut with the center of an end mill. It's not designed for that. Okay, and it has helical flutes similar to a drill, and they function similar to a drill where they can actually auger material out. But the edges of an end mill actually can cut as well, so you can side cut with that. And also, you can change the number of teeth that you have in an end mill. You could have 7, 8, 9, flutes, however many make sense, and there are advantages and disadvantages to doing that. And again, end mill design is probably even more expansive than drill design, although you could get a career literally doing either and designing them. And there are a lot of different tools that are meant for different, some are meant for very different, very specific applications of material and load of how much material they'll take out and under what conditions. And they're very, very specifically made, and they can be made of high-speed steel as well or carbide. You can have end mills, types of mills that have inserted teeth on them. Although generally, I would say most end mills are either made of solid high-speed steel or solid carbide. So nowadays, obviously, carbide's preferred, but there are reasons for still using high-speed steel end mills, and they are still made and they're still used. And then taps. We're just going to kind of throw this in here too because it kind of makes sense. These are the drills, mills, and taps are kind of what you see in general machine shops. And why do you use a tap? Well, I use a tap to make a screw thread. So we'll talk about thread milling too. That's kind of a newer way to do things. Now we have CNC machines that can be very repeatable. You can actually do a thread mill, which actually is a type of end mill that makes a thread form. Okay, and it can either be multi-point or single point. But a tap is the good old-fashioned way of, you have a hole, you drill a hole, or you interpolate a hole, and then you run a tap through it, and a tap puts a screw thread into the hole. Okay, and there are a lot of different types of taps, and there are different methods. There are cut taps, and actually I have a good video in here of forming taps, and you should look at the form tap video. It's a way of making the thread form slightly differently without cutting material. You kind of roll the material into place, and it makes a stronger thread. So, taps, again, is a whole industry around taps, but they're a type of cutting tool in general, and they are used very specifically to make those screw threads so you can attach screws to things. And they've been around for a very long time, ever since the first Bridgeport mill was made, knee mill was made, we've had taps, and they precede that. And a tap is a very convenient, easy way to take a hole and make it threaded for some sort of screw or some sort of bolt. Okay, because again, remember, in most cases, for most tools, for most tool design, the things we're talking about, there are all kinds of different things that can be made. But in general, you're going to be talking about a lot of things that look like rectangular blocks with holes and slots in them. Okay, and some of those holes are going to be threaded for bolts and screws to go into. So if you have drills, mills, and taps, and you have a CNC machine, and you have some rudimentary, fixturing system, some sort of Kurt vise or something, now you can start to make a whole lot of really, really useful things with that. Okay, so I think it's important to understand, these three categories of tools: drills, mills, and taps, and just at least have a general understanding of how they work. Okay, so if you have any questions, please call, text, or email me. Thank you.